Fission, homework A. Number 1. Fission occurs when an atom is so big that the attractive blank force cannot reach well enough to overcome the repulsive blank force. Remember, inside the nucleus, we have protons next to each other, and all those protons are positively charged. By their electric nature of positive charges, the electromagnetic force is going to be pushing them apart. They would normally fly apart if it wasn't for the strong force that was pulling them together. The strong force can't reach very far, though. So if you have a very big nucleus where these protons are far apart, the strong force can't quite reach to hold them firmly in place. However, the electromagnetic force can reach that far and push them apart. So for problem number 1, the answer is option A. The attractive strong force cannot reach well enough to overcome the repulsive electromagnetic force. Number 2. When fission occurs, blank are released. These shoot out and hit other atoms, causing them to fission. Okay, we have a large nucleus, and as it goes through the fissioning process and it breaks in half, we're going to have several things fly off. Depending upon the kind of atom it is, it might be 3, it might be just 2, maybe 4, but all these things that are flying out independently are neutrons. And these are pretty massive particles compared to electrons. They're slightly bigger than a proton. So when these hit other unstable atoms, these neutrons will cause those big atoms to break as well. Number 3. A blank is when one fission reaction causes another fission reactions to occur in ever-increasing numbers. That's going to be D, a chain reaction. Just like a chain has lots of links where one link leads to another link, leads to another link. In a chain reaction, one fission reaction leads to another fission reaction, which leads to another, and usually multiple times. Number 4. Suppose uranium-236 fissions to make an atom with 52 protons and 83 neutrons. It releases 3 neutrons at the same time. What is the daughter isotope? There's lots of extraneous information here that we do not need. We're going to start off with uranium as the initial material. That's known as the parent isotope. And from the periodic table, we can see that uranium has 92 protons. So I'm going to put 92 down there. This 236 is how many total things are in the nucleus, both protons and neutrons. For this kind of a problem, we're only concerned about protons. The reason for that is it's just the protons that are used to identify an isotope. We want to identify the daughter isotope. Okay, so we start off with uranium with 92 protons. We end up with an atom with 52 protons. What atom is that? So I look at the periodic table, and it's right here, Te. It's not terribly important what the name is, but just to make things look pretty, I'm going to write it down. The primary thing that we want to know is this number down here. How many protons are in this other element? We started off with 92 protons. One of the daughter isotopes has 52, so that means that we have 40 that are still unaccounted for. So the other atom has 40 protons. And from the periodic table, that's going to be zircon, Zr. We don't really need to put any of the other numbers around these letters. So letter A is our answer. Number 5. Suppose that uranium-238 Okay, this is slightly different than before. It's not 236 anymore, it's 238. It's a different isotope. That's okay. Lots of different isotopes of uranium exist. Okay, U-238. We start off with the U, and it still has 92 protons. That doesn't change. All uranium have 92. Okay, it fissions to make an atom with 58 protons. So we have the arrow, 58, and that is from the periodic table, Ce, plus something else. So I take my calculator and I subtract 92 minus 58, and I get 34. So we have 34 other protons in our daughter isotopes. And from the periodic table, number 34 is Se. And that would be option D. Number 6. In a nuclear explosion, 100 kilograms of fuel is used. Of that fuel, only 0.0001 kilograms of matter is turned into energy. How much energy was in the explosion? Again, there's some extraneous information here. The thing that we need to know is how much matter was turned into energy. The other matter is not important. So the 100 kilograms is not going to be used here. We're going to use Einstein's equation to figure this out. The E is what we're trying to find. The M is the amount of mass that's converted, 0.0001, that has to be in the kilograms. And the C is the speed of light, 3 times 10 to the 8th, and we have to square that. Don't forget to square it. So, our calculator. I think it's kind of important to use the EE button or EXP button on your calculator in order to have things work out right. It's not absolutely required, but it's easier to make mistakes if you do it other ways. So, the mass, 0.0001 kilograms, times the speed of light, 3 EE, EE to the 8th, and then I hit the squared button. Hit enter, and there's the answer, 9 times 10 to the 12th. So 9 times 10 to the 12th is a 9 with 12 zeros after it. So here's hundreds, thousands, millions, billions, trillions. 9 trillion is the answer, and 9 trillion will be between 10 billion and 100 trillion joules. Number 7. In a very, 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 very tiny nuclear reaction, only 100 joules of energy is released. How much matter was converted to energy in this explosion? I'm going to be using Einstein's law. And the E is 100. The M is what we're trying to find. And the C is the speed of light. 3 times 10 to the 8th. And we have to square that. So I'm going to square this first of all. That's going to be 9 times 10 to the 16th. And then I'm going to divide both sides by that scientific notation. So 100 divided by 9. Oops, let me clear that out. 100 divided by 9, EE 16, but I have to have that squared. And so I get a number that is much less than 0.000001. Number 8. In a 400 kilogram nuclear bomb, 0.0000053 grams. Let's make sure this is kilograms. Make sure in your packet it says kilograms after that decimal number. Okay, that much of matter is turned into energy. How much energy was released in the explosion? Einstein's law. We want to know the E. The M is our tiny decimal number. The C is the speed of light. And I have to square that. So getting out my calculator, 0.0000053 times 3 EE 8, and I square that, equals 4 times 10 to the 10th. So that means that I move this decimal point over 10 places. 2, 3, 4, 5, 6, 7, 8, 9, 10. So hundreds, thousands, millions, billions. 47 billion. So 47 billion is going to be option C, between 10 billion and 100 trillion joules. Number 9. In a small nuclear explosion, 900 trillion joules of energy is released. That sounds like a lot of energy, but for a nuclear explosion, that's tiny. How much matter was converted to energy in the explosion? So, Einstein's law. The E is the 900 trillion. There's trillion, billion, million, thousands, hundreds, equals the M that we're trying to figure out, and then the speed of light, 3 times 10 to the 8th, and we have to square that. So dividing 900 trillion by that scientific notation squared. Let's first do the scientific notation squared. We'll get 9 times 10 to the 16th. And the 900 trillion, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's 9 times 10 to the 14th. So that shortens things up here a little bit better. Type that into the calculator. 9 EE 14th divided by 9 times 10 to the 16th. 9 EE 16 equals 0.01. So 0.01 is not more than 0.1. 0.01 is not smaller than this number, so it's option C. This number is smaller, this number is bigger. Number 10. An isotope has this notation. How many protons does it have? Remember the top number, top right is the number of the net charge. Bottom right is the number of neutrons. Top left is neutrons and protons together, total things in the nucleus. And this down here is the number of protons. So option C is the right answer. And unfortunately, I do not have the second page for the homework, so I have to stop right there. If you have any further questions on the problems that remain, you'll have to ask in class.